everyone. We are powering a weather station using solar energy and measurement of solar irradiation and UV rays team. I am Kayla Garcia.
I'm Paxton.
I'm MD Shafqat Rahman.
And I'm Altai. In weather stations, sensors are employed to collect data about the environment. There are multiple measurements of interest like temperature, wind speed, wind direction, wind chill, rainfall, humidity, air pressure, visibility, irradiation, air quality, and heat index, and others. As part of our design project, we have worked with our colleagues to design, build, and test a portable weather station. For it to be deployed in a location where power is not readily available, it needs energy storage with a renewable energy source to recharge it. The battery and renewable source must regulate and distribute power to all sensors. This report discusses the design of the power portion of the weather station.
For a background, the photovoltaic effect was discovered in 1839. Silicon was used to create a solar cell later on, and today many technologies rely on solar energy for power, including both DIY and professional commercial weather stations like the Davis Pro 2 weather station. Power electronic charge controllers are used to regulate the power coming from a solar panel. They employ either pulse width modulation or maximum power point tracking, and these two algorithms work in two different ways. The UV index was invented in 1992, and the first global UVI was standardized in 1994. Solar irradiance was invented in 1893. Space-based observations of solar irradiance began in 1978 with the Nimbus 9 satellite. Today, pyranometers and pyrheliometers in the market are ground-based, but they measure solar irradiance very accurately.
Here's the experimental setup is our block diagram. Looking at it from left to right, the solar panel harnesses energy from the sun, producing up to 21.6 volts. The solar charge controller regulates the solar panel's power to charge the battery and the weather station. The output voltage of the solar charge controller flows to the battery, which is 11 to 14.8 volts, and the battery takes over if the solar panel cannot provide enough power. The communications board provides 2.3 volts and 12 volts needed to power our two sensors. The UV sensor and solar radiance sensors measure UV radiation and solar radiance. The solar radiation sensor requires signal conditioning to drop the voltage from 5 volts to 3 volts.
For our test plan, we got together with all the groups and got the total power required to power all the sensors simultaneously. And what we considered was at least 5 watts of additional power for a safety margin. To test the solar panel, a multimeter was used to measure the voltage and the current, and that is produced under various weather conditions. The solar charge controller was tested with and without the solar panel, and a multimeter was used to measure the voltage and current to find the maximum power point tracking and its control efficiency. The code was developed to be used to the communications board to interpret the analog voltage reading from the UV and the solar irradiance sensor. Both the UV sensor and the PG solar irradiance sensor were tested in the same fashion. It was powered at different times of the day, and the output voltage was measured using a multimeter.
Our results from these experiments are shown here. Our solar panel, the JLM50, has a power rating of 50 watts. Here, there's the current voltage relationship and the power curve under 4 different conditions. Sunny, under tree cover, extra sunny, and cloudy. The solar charge controller was able to operate with just over 90% efficiency, and when the solar panel's output voltage dropped to the voltage of the battery, the efficiency of the charge controller lowered, and it stopped providing charge to the battery. The PGFUM solar radiance sensor and the UV sensor were both tested at different times of the day, and were up to 95% accurate.
So to test, we conducted testing on our power system and sensors at different times of the day. The solar panel could power weather station and the battery. The solar charger controller could track MPP with over 90% efficiency. When solar panel could not provide power, the battery took over. And the two solar sensors gave accurate results with at least 75% with 70% accuracy. So all in all, the desired outcome of powering the weather station, charging the battery, and sending accurate readings from our UV and solar irradiance sensor was achieved. Thank you.